Okay, thank you very much, Jeff. Yeah, my name is Rohinton Emmanuel. I'm from Glasgow, Caledonian University. I make this presentation on behalf of Oksana and Nieva, Mushfik Jalal, and Narein Pereira from University of Moratuwa, Sri Lanka. Okay, I wish to start talk to about uh, the lessons from a few of the our attempts to do mapping, heat mapping in different cities, and say something about some of the lessons at the end. As you know, of course, this is IAUC meetings, ICUC, so I don't have to say. It is increasing heat risks, that is already known. Given that, so we have IPCC's definition of the risk. Risk is a function of hazard uh, modulated by exposure and vulnerability. So in our case, of course, the risk here is the heat or high temperature, and the intermediary effects of built environment is the thing that modulates uh, the exposure. Of course, then socioeconomic factors then lead to the vulnerability. So, in developing cities, given the weak infrastructures, poverty, and also the aging population, uh, poses specific risks. But in the case of developed cities, in addition to these things, perhaps health inequity, which is also there in developing cities, but it's a specific problem. And if you are talking about temperate climate, the climate change related lack of awareness also is a problem here. And finally, therefore, we need to also see the local variations in urban heat risk. So that was the attempt here to map it, right? So what have we done? So what am I talking about? I am going to present a few studies that we had done, three in this case, or prior work on heat risk mapping. This is in two in developing countries and one in my own back home country. Colombo, Sri Lanka, as the developing city with rapid on the cusp of rapid transformation. It hasn't undergone rapid transformation yet. It about to go undergo. So this is why I thought it'll be interesting to see the results from there. Dhaka, Bangladesh, of course, is probably the fastest growing developing cities. Dhaka grows as the city is being watched. So here the problems, although it's developing, it has other issues of speed. And finally, Glasgow. It's a mature city which has had its urban decline already and it's coming up a little bit, but there is historic inequity. And so we thought it'll be interesting to see what lessons could be learned. So I will then present the workflows and some of the challenges, lessons, and maybe perhaps some future directions. And I'll leave it at that kind of stuff. So results. Here is Colombo's work. What we did here was to look at the physical environmental factors. And you see on the left side the data that we use for the physical factors. On the right side are the socioeconomic factors. On the left, you see impervious surface function because it is a very wet climate. It's hot, humid, and therefore the wetness is a issue. It will be useful. The LST is the only temperature data that we can get at finer scale. That is a problem. So I'll say something about this in the pitfalls and lessons learned. NDVI, as you know, that NDVI itself is not a vegetation quantification. It's a quality indicator, but that is the only thing that is available. And then in this case, because of the wetness and the amount of rainfall, soil moisture, we knew from previous work that might be of value. And we also had access to some GIS data, building density, uh, sky view, and the green and blue infrastructure, given the water availability. On the right side, you have the various census data at very fine scale also. Total population, sensitive population, And one of the things that they do very regularly is the housing type, house condition survey. The condition survey gives something about the type of house, and therefore you could use that as a proxy to uh, various socioeconomic factors. So the model looks something like this. The physical environment is the left one that I just mentioned. And on the right, you have the socio-economic variables. We reclassified them to the same scale. And we used expert opinions, on an analytic hierarchical process to come up with a weighted overlay and then a heat map. And the map looks something like this. So that is the municipal area of Colombo. The red is the highest heat risk, and the green is the lowest heat risk. It kind of makes sense by some kind of uh, ground truth verification. And the middle you have the most green, leafy suburbs, and then you have the shantytown slums on the upper center, and that kind of makes sense. And on the left, you see the correlation between the variables. Not everything is highly correlated, so it's also useful here to see that these many variables may be useful also. Dhaka, Bangladesh, we took a completely different approach. It is a city that is growing super fast. So here the decisions have to be made yesterday or day before yesterday. So that in order to do that, what is the it's the planning decision making that is necessary. They are one of the few developing cities to have a heat officer, first, probably the first in developing world. So here our attempt is to look at which areas of the city they should keep and which ones they could probably look to improve. So similar kind of data, land use, land cover, LST is the only temperature data we can get detail, but here the socioeconomic data availability is slightly different. They have average household size and the thing called affordability of housing. So that's a proxy for socioeconomic variables. On the physical side, very similar to Colombo. And we were able to then map this on a socio-economic versus physical environmental factor axis. So you have these four quadrants: low socioeconomic, low physical, and the bottom left means on the right side you could see what it means. It means it is suitable for population growth. This has area, which you can see it is industrial, and so forth. So this is an area where you can afford to grow. And on the diagonally across high socioeconomic and high physical, that means this is here physical space could be used to reduce climate, the warmness, because it has the physical asset, so to speak. The other two are problematic areas. So that's perhaps where you either don't allow any development or you focus on other development. So here, as you can see, the approach is slightly different because they are not really interested in mapping the heat risk. It is about planning decision making. Uh, Thirdly is Glasgow. In the case of Glasgow, Glasgow's 2050 climate would be current London climate, and London already has a very significant heat island problem and death. So this is a preparatory work here. So on the left, you have your physical environmental variables, and on the right side, we had the socio-economic variables. This is part of a larger study, and the city is in the process of converting many of the city center streets into tree-lined avenues. So we were looking at that also, but I'm not going to talk about that part, but it is the mapping part here. Right? So very similar kind of data, but slightly different here. Surface LST data, but there is three-dimensional building data, slightly more stuff available, building volume, building height. And so looking at those, here is the model. Yeah. So the workflow. So we did two things. We looked at typical summer and very hot summer. 2018 and 2020 were really hot summers. So you could see what difference that it would make. So a surface urban heat island again. So I'll talk about the limitations of this approach in a minute. But that's the workflow you see on the slide now. Plotting this together, you get of these kind of images. the key one here is C, but the bottom left. And so you could see what happens to the clusters of heat or hotspots during normal summer 2018 to 2020 and a heat wave summer. It's slightly different. So this is also an important variable here to keep an eye on. On the right, B is the hotspots themselves. And at the bottom is the relationship between the R squares of the geographically weighted regression between green infrastructure and the surface urban heat island. And you can see that the sort of the small bits of green patches that we have left is the key bit that have. Okay, so what lessons have we learned from these three attempts? First is, I think, is the need for standardization. You can see that we ourselves did three different parts of work and we did completely different processes, largely because of availability of data. So we need probably to standardize this heat mapping approach. If we are going to standardize heat mapping, then what should be covered? That is a question that we need to also uh, rationalize. Perhaps this is for something for IAUC also. Secondly, of course, the need for local expertise. Without that, it'll be impossible. That goes without saying, I think. To contextualize risk is a local variable, local feature. So the how do we appropriately ascertain the amount of risk is you need local expertise. Thirdly, as I said before, also we have been using LST, low land surface temperature, which is okay. I need to stop. So I'll just present the overall slides in here. Right? So define the purpose. Why? What is this for? Are we doing this for heat planning or is it for forecasting? That also needs to be understood. And finally, I think a few things to say about how do we go forward. Risk mapping is a function of hazard, vulnerability, and uh, exposure. Should we equally weight them? If IPCC does not say what the weightage has to be. So that's another question to ask. What is the appropriate resolution needs to be also answered. And how should we visualize it? Right? So the lessons for future is the sensitivity analysis is very important. That we need to do how do we present this data, because every time you make slight differences, you get completely different results. This modified aerial unit problem is a huge problem. The way we cut borders would be also very important to understand. And vulnerability mapping itself is a learning process. It's not an end. I think the key part is the process of mapping it, not the actual map itself. And finally, some references that say something about this. So here, there is nothing called no risk situation. So we have to define the acceptable risk, and not creating the risk in the first place is probably even more important than mapping it and then trying to solve a problem having created it. Thank you very much.
Okay, thank you very much for a nice presentation.